Okay, next we go into measures of dispersion. Measures of dispersion. The word dispersion means kind of variability. And if you look at those two data sets, as your discussion board post basically said, they do have different measures of dispersion. The most simple measure of dispersion that we sometimes use is called the range. The range is basically coming from the lowest number to the highest number and the difference thereof. So in data set 1, going from 1 to 3, a range of 2, 0 to 4, a range of 4. There are more mathematical ways to compute that, but basically the range is one measure of dispersion to use. But we don't use that very much in a statistical sense. It's just really an eyeballing type of situation where you can look and see one has more range than the other. The thing that we'd like to do, and the thing I have to take you through now just a little bit, is we'd like to do something a little more mathematical than that. So one of the possibilities of what we could compute, it looks like it's on page 107, but I have it in the notes here, the sum of the deviations from the mean. See if you can figure out in data set 1 the sum of the deviations from the mean. And by the way, the formula there, x represents one score, u or mu represents the mean for that population. So you'd basically do in data set 1, it would be 1 minus the mean, which is 2, plus 2 minus 2, plus 3 minus 2. And if you were to add all that up, do the hokey pokey and turn yourself around, that's what it's all about. Oops, sorry, a little funny there. The idea would be that if you added all that up, the sum of the deviations from the mean for that data set would be 0. Because 1 minus 2 is negative 1, 2 minus 2 is 0, 3 minus 2 is 1. How would it be for data set 2? Can you figure that one out? 0, 2, and 4? Hopefully you came to the same conclusion. 0 minus 2 is negative 2, 2 minus 2 is 0, 4 minus 2 is positive 2. So the sum of the deviations from the mean, by definition, are always going to equal 0, and you should know that. So that's interesting, but it's not really statistically useful, because if we look at those two data sets, we'd want data set 2, the measure of dispersion, to be a larger value, and it's not here, it's always 0. So one way we can fix that problem is we can square things, because the problem with the reason we always get 0 is because we keep doing negative 1 and positive 1, and they add up and they always equal 0. So one idea is take the sum of the square deviations from the mean. And so in that situation, it would be one score minus the mean squared and add it up. So let's go for data set number 1. So you would do 1 minus 2. Quantity squared is what? 1. 2 minus 2, quantity squared, still 0. 3 minus 2, quantity squared, is 1. Squared is 1 again. So if you add all those up and do the hokey pokey and turn yourself around, wonder if hokey came from, no, we are in Virginia Tech territory. Never mind. The sum of the squares then for this data set, for data set 1, would be 2. It would be 1 plus 0 plus 1. So the sum of the square deviations for data set 1 would be 2. Can you figure out what it would be for data set 2? 0 minus 2, quantity squared, so that's 4, plus 2 minus 2, quantity squared, 0, plus 4 minus 2, quantity squared, is 4 again. So if you add all of that up, then you're going to get a result of 8 for that particular situation. So hopefully that makes good sense. So in this particular situation, the sum of the square deviations for data set 2 is 8, and for data set 1, it is 2. So this is our first useful measure of dispersion. It's called the sum of the square deviations, abbreviated sums of squares. The sum of the square deviations is you take a score, you subtract it from the mean, and you square it. We square it to get rid of negative values. Then we add it up. And in this case, the sum of squares for data set 1 population is 2. For data set 2, it is 8. So there is more dispersion by the measure of sum of squares for data set 2. So that's considered statistically useful. Okay, that'll cover this recording. Thanks. Bye-bye.